All right, in this video, I'll be going over section 8.4. Section 8.4 is about differentiating and integrating power series. Okay, I want to start with this theorem 8.11 in the textbook, differentiating a power series. Okay, here is the statement of the theorem. If sigma k goes from 0 to infinity, ak times x minus x naught to the power k is a power series in x minus x naught that converges to a function f of x on the interval I, then the derivative of f is given by f prime of x is equal to the derivative of this power series. Okay, to get the derivative of this power series, what you can do is you can differentiate term by term. That's what this inequality tells us. Or in other words, you can send this differential operator inside the summation sign. Okay, as you can see, I have moved my derivative operator inside the sigma symbol. So now what you really do is here is that you differentiate the series, this original series, term by term. That's what we mean by moving this differential operator inside. Okay. Now this is if you differentiate this one, this expression with respect to, of course, this is a constant. So I can apply the derivative operator d over dx to only to this term. So if you differentiate this term, what would you get? That is k times x minus x naught to the power k minus 1, right? So that's what you have here. That is k times, k is here, of course, k times x minus x naught to the power k minus 1. And this ak is a constant that stays as it is. Okay. So all what this tells you is that if a function is equal to its power series, then to differentiate your function, you can differentiate your series. To differentiate your series, you can differentiate your series term by term. Or in other words, you can send this derivative operator inside the sigma sign. Okay. And then if you differentiate the inside term, this is what you get. You get this summation. And then the interval of convergence for this new series is I, with the possible exception that if I is a finite interval, the convergence at the endpoints of I may be different than it was for the initial series. Okay, the convergence of this new series at the endpoints may be different from the convergence of this original series. You need to check what happens at the endpoints for this series. All right, to understand this theorem, let's go over an example. Here is the example that I want to look at. Using the derivative to find the Maclaurin series for 1 over 1 minus x squared. Okay, how do we use derivatives? Or in other words, how do we use this theorem to find the Maclaurin series for this particular function? What I'm going to do is, if I want to apply this theorem, some sort of a derivative should be involved, right? So what I'm going to do is, I'm going to view this function as a derivative of a function whose Maclaurin series is known. Can you think of this function as the derivative of a function whose Maclaurin series is known already? What about this function? What about this function 1 over 1 minus x? Let's try that function. The good news is that we know the Maclaurin series of this function by previous sections. Okay. So what would you get if you differentiate this function? D over dx 1 over 1 minus x. What would you get? This is exactly 1 minus x whole thing squared, right? That is exactly this function, the given function. We are asked to find the Maclaurin series for this one. So now we know that the derivative of this function is this desired function. Now we know the Maclaurin series for this function. What is the Maclaurin series for this function from previous sections? 1 minus x is nothing but sigma k goes from 0 to infinity x to the power k. That's the Maclaurin series. Okay, so now we can apply the previous theorem. Remember, we need the derivative of this function, right? But that function is equal to its Maclaurin series. To get the derivative of this function, all what you need to do is to you can find the derivative of the summation. To find the derivative of the summation, you can find the derivative of each and every term. Or in other words, you can send the derivative operator inside. So let me write this series notation over here for this one. I'm going to replace this function by this Maclaurin series representation. So I'm going to have d over dx sigma k goes from 0 to infinity x to the power k. This is what I need. Okay, that's exactly equal to the function that is given to us. Okay, so now to get the derivative of this one, we can apply the previous theorem. Remember, from this inequality, you can send this derivative operator inside. Okay, so now I can send this derivative operator inside the summation. This should be equal to, this should give us from the previous theorem by theorem 8.11, we have sigma k goes from 0 to infinity d over dx x to the power k. That's what you have inside, right? Inside sigma, you have x to the power k. You take the derivative of that. That is nothing but sigma k goes from 0 to infinity. Let me write here, this is equal to actually 1 minus x, 1 over 1 minus x squared. Okay, that is this term. So now I can take the derivative of that one. That is sigma k goes from 0 to infinity k times x to the power k minus 1 is equal to 1 over 1 minus x squared. That gives you the Maclaurin series of the given function. This is the given function that is equal to this summation. That is the Maclaurin series of the given function. Now, the next question is, how do you find the interval of convergence? By the way, this summation goes from k is equal to 1 to infinity, okay, not 0. Over here, it should be k goes from 1 to infinity. Why is that? Why is 1 there, not 0? Because in this series, you had k is equal to 0, right? That's because when k is equal to 0, this is 1, right? The derivative of 1 is 0. So that term vanishes. So really, k goes from 1 to infinity, k times x to the power k minus 1. All right, so we have the Maclaurin series for 1 over 1 minus x squared. Now we need to determine the interval of convergence. Okay, how do we find the interval of convergence? From the previous theorem, we know that the interval of convergence for this series is the same as the interval of convergence of the original series. Original series was this one. Okay, except for the possible, with the possible exception that at the endpoints, the convergence of this series may be different. Okay, first of all, what is the interval of convergence for this series? Clearly, this is a geometric series, right? For a geometric series with r is equal to x, this is your r, right? For this geometric series. So this converges when absolute value of x is less than 1. That is, x is between minus 1 and plus 1. We have seen this many times. So that's the interval of convergence for the original series. So the interval of convergence of this new series includes this interval, but you need to figure out what happens at the endpoint. At x is equal to minus 1 and x is equal to 1. What do you do? What is the standard procedure? You try out the series at each endpoint when x is equal to minus 1. Let's try minus 1 first. What you do is, in the new series, this is the new series. In this new series, I'm going to plug in x is equal to minus 1. If I plug in x is equal to minus 1 in the new series, what would you get? Sigma k goes from 1 to infinity k times minus 1 to the power k minus 1. Okay, now we need to check whether this series converges. Okay, what do you think? Would this series converge? This is clearly not convergent because if you think of this term AK, the general term, what is limit as AK, K goes to infinity, as K goes to infinity, AK. Is this zero? If it is convergent, this should be zero, right? If this is not zero, then by divergence theorem, this does not converge. Okay, this series does not converge. Okay, so what do you think? What would be the limit of this one? Would this limit exist as zero? Clearly not. That's because this limit does not exist, because as you can see, the sign is alternating. Here you have minus 1 to the power k minus 1. Okay, you can plug in k is equal to 1, 2, 3, 4, so on and so forth. As you can see, this sign is changing, plus minus, and this k is growing. Okay, while k is growing, the sign is changing. So that means this does not approach to zero as k goes to infinity. That means ak does not approach to zero as k goes to infinity. This is not equal to zero. Hence, by divergence theorem, if this limit is not equal to zero, there is no way that this series converges. Okay, by divergence theorem, series diverges. Okay, again, to see that this is not equal to zero, you can expand this series. Okay, you can write down few terms for AK. The first term, when k is equal to 1, you get, what would you get? Just 1. And then k is equal to 2, you get minus 2. And then 3, when k is equal to 3, you get just plus 3. And then minus 4. And then plus 5. Minus 6, so on and so forth. As you can see, these numbers are getting bigger and bigger. The magnitude is getting bigger and bigger, but the sign is switching. Okay, so that means this never converges to zero. This is not equal to zero. So by divergence theorem, this series diverges. Okay. Similarly, you should be able to see that at the other endpoint, when x is equal to 1, your series becomes k goes from 0 to k goes from 1 to, pardon me. If you plug in x is equal to 1 in the new series, you get k times just k, actually. K goes from 1 to infinity, just k. What is this? Again, clearly this diverges, because if you take your AK limit as k approaches to infinity, your AK is not equal to 0. This is your AK, by the way. That's clear, because as k approaches to infinity, this k approaches to infinity. It's not approaching 0. So by divergence theorem, the series diverges. By divergence theorem, series diverges. Okay, so the interval of convergence of the new series is minus 1, 1. That completes that example. Next, I want to show you how to integrate power series. Okay, if a function is equal to its power series, then we need to be able to see how we can integrate that function and the power series. Okay, so here is the statement of the theorem. This is theorem 8.12 in the textbook. Integration of power series. Let sigma k goes from 0 to infinity ak times x minus x naught to the power k be a power series in x minus x naught that converges to a function f of x on the interval I. Okay, that converges to a function f of x on the interval I means this function is equal to its power series. That's what it means. Okay. Here is the conclusion. The indefinite integral of f is given by indefinite integral of f of x dx is equal to the indefinite integral of the power series, which is equal to sigma k goes from 0 to infinity ak times the indefinite integral of x minus x naught to the power k. Okay, what that tells you is that you can send this integral sign inside the summation. just like what we did in the differentiation case. Remember, we were able to send the derivative operator inside the summation sign. Here also, we send this integration sign inside the summation, okay? I'm going to send that integration sign all the way up to here because this AK is a constant, so it can stay outside. So integration sign comes here, okay? That's what it tells you. And in fact, if you integrate this with respect to X, this is what you get. X minus X naught to the power K plus 1 divided by K plus 1. That is the integration of X minus X naught to the power K. And plus a integration constant. Remember, when you do the indefinite integral, you have to put a integration constant, right? That's what this constant is about. And then here is what we can say about the interval of convergence. We can say a similar thing as in the derivative case. The interval of convergence for this new series is I, with the possible exception that if I is a finite interval, the convergence at the endpoints of I may be different than it was for the initial series. Okay, the convergence of this new series at the endpoints may be different from the convergence at the endpoints of the original series. Okay, so you always have to check the endpoints for the new series. All right, let's look at an example to understand this theorem better. Well, before I go over an example, let's go over the second part of this theorem. This is the first part. This is for indefinite integrals. This is how you integrate the power series. And then let's look at the definite integral case. Okay, here is the next part. If C and D are 2 points in the interval I, which is the interval of convergence for the power series, then the definite integral of f on the interval c comma d is given by definite integral of f of x from c to d dx is equal to the definite integral of this power series from c to d, which is equal to sigma k goes from 0 to infinity ak times the definite integral of this inside term. Okay, what that again tells you is that you can send this definite integral inside the summation. When I send it inside, I send it all the way up to here because this ak is a constant term. Okay, as you can see here. And of course, if you now integrate this term, if you calculate this definite integral, this is the notation, limit notation for the definite integral. Notice that this is going to be x to the power k plus 1 divided by k plus 1. That is exactly this. And then you plug in the limits, lower limit and the upper limit. And if you plug in those limits, this is what you get. Okay, you can easily see it. Here, notice that k goes from 0 to infinity. Here also k goes from 0 to infinity, unlike in the differentiation case. Remember, in the differentiation case, here k goes from 0 to infinity, but here k goes from 1 to infinity. Why was that? Because if you take the first term, when k is equal to 0, this is a constant. The derivative of the constant term is 0. So you don't have to start the indexing with 0. So you started the index at k is equal to 1 in the derivative case. But here, in the integration case, you get something when you integrate when k is equal to 0. So the indexing starts at k is equal to 0. All right, let's now look at an example. Here's the example that I wanted to go over. Using the integration to find Maclaurin series for ln1 plus x. Remember, we are going to use integration. That means we are going to use one of these theorems. This theorem or this theorem, okay? I mean, this part, first part of this theorem or the second part of that theorem. Find the Maclaurin series for ln1 plus x. How do we find the Maclaurin series? Well, if we are planning to use the integration, you need to somehow view this function as an integration of a function whose Maclaurin series is known. In the derivative case, remember, we wanted to view the given function as the derivative of a function whose Maclaurin series is known. In this case, you need to view this given function as the integral of a function whose Maclaurin series is known. Can you think of a function whose integral is this function, and you know the Maclaurin series. Well, let's think about this function. Okay, what about this function? If we can find the Maclaurin series of this function, notice that the integral of this function, integral, say for example, integration from 0 to x 1 over 1 plus t is exactly ln 1 plus x, right? Of course, I'm plugging limits, okay? The integration of this is 1 ln 1 plus t, and if you plug in the lower limit and the upper limit, you will get exactly ln 1 plus x. Because when you plug in the lower limit, it's 0, right? ln 1 is 0. So this is what you're going to get. All right, now, but the problem here is that, do we know the Maclaurin series for this function? We don't quite know the Maclaurin series for this function, but we know the Maclaurin series for this function, 1 minus t. We know this one. This is the one that we used in the previous example. This is k goes from 0 to infinity, x to the power t to the power k, right? K to the power e to the power k. Okay, that's the Maclaurin series. Now the question is, can we use this Maclaurin series to find the Maclaurin series for this function? Because this is the function that we need to find the Maclaurin series of the given function. We need to find the Maclaurin series for this given function. So if we know the Maclaurin series of this one, we can use the previous theorem to integrate that Maclaurin series over here. Okay, so let me find the Maclaurin series for this one using this one. What I'm going to do is I'm going to replace my t by minus t. Replace t by minus t. That will give you 1 plus t. That becomes minus times minus t is equal to sigma k goes from 0 to infinity minus t to the power k. I'm just replacing my t by minus t in this expression, in this equation. Okay, then you get this becomes 1 over 1 plus t. That's what exactly you need. That is equal to sigma k goes from 0 to infinity minus t to the power k, or you can write minus 1 to the power k times t to the power k by applying the minus k power for each term to minus 1 and t. All right, now what is the interval of convergence for this one? This is again a geometric series, right? With your r is this inside term. This is your r in this case, okay? So clearly the interval of convergence is minus 1 comma 1 again for this series. Okay. Now, since I know the power series of this one, now I can use this equation to find the Maclaurin series for this function. Okay, so all I'm going to do is I'm going to plug in this series over here, and then I can integrate that series using the previous theorem. By previous theorem, I can send this definite integral inside like this. Okay, I can send this definite integral inside. So let me do that calculation. So integration 0 to t 1 over 1 plus t dt. I'm missing dt here. Is equal to sigma. Let me write the full statement. Integration from 0 to x, pardon me, here it should be 0 to x. Okay, as we just have here, that is going to be 0 to x. 0 to x. I know that 1 over 1 plus x is sigma k goes from 0 to infinity minus t to the power k dt. All I'm doing is I'm replacing this by this summation. That's what I found here. Okay. Now I send the integral sign inside. This is going to be sigma k goes from 0 to infinity, integration from 0 to x minus t to the power k dt. Now I can integrate this one, this expression. Okay. If I integrate this from 0 to k, I can evaluate that. That is going to be sigma k goes from 0 to infinity Actually, before you integrate that, notice that this piece is equal to minus 1 to the power k times t to the power k, right? You can apply the kth power to each individual term, then you get that is minus 1 to the power k times t to the power k. Now you can take the integration. Pardon me, you are taking the integration here. This is a constant. So you all what you need to do is take the integration of this one. That is going to be minus 1 to the power k stays as it is. The integration of e to the power k from 0 to x will be x to the power k plus 1 divided by k plus 1. I'm plugging the limit, okay? I'm calculating the integral. That means if you integrate this one, you get t to the power k plus 1 divided by k plus 1. And then the lower limit is 0, upper limit is x. If you plug in those limits, this is what you get. Because if you plug in lower limit, it's going to be 0. So only this survives, okay? So this is the Maclaurin series of the given function, ln of 1 plus x, because this is nothing but the integration from 0 to x, 1 over 1 plus t dt. Okay, so let me write. Putting all these together, 0 to x, 1 over 1 plus t dt, which is exactly ln 1 plus x, is equal to this power series. Okay, that's going to be sigma k goes from 0 to infinity minus 1 to the power k. Move this little bit to the left, times x to the power k plus 1 divided by k plus 1. That's the Maclaurin series of the given function ln 1 plus x. Okay. So now how do you find the interval of convergence? Remember the interval of convergence of this series. Interval of convergence for this series was minus 1 comma 1. Okay. So to find the interval of convergence of this series, you need to analyze the endpoints, okay? Because the interval of convergence of this series includes minus 1 comma 1 open interval, but you need to analyze what happens at the endpoints, okay? So let's do that as a separate analysis. When x is equal to minus 1, you plug in x is equal to minus 1, it becomes, the series becomes sigma k goes from 0 to infinity. You put minus 1 for x, then you get minus 1 to the power k minus 1 to the power k plus 1 divided by k plus 1. Okay, this is going to be, what is this going to be? Minus sign will work out because minus 1 to the power k times minus 1 to the power k plus 1, which is minus 1. Sigma k goes from 0 to infinity 1 over k plus 1. This is nothing but minus 1 times. You can change the indexing. K goes from 1 to infinity 1 over n, 1 over k. This is the harmonic series, right? This is clearly the harmonic series. This diverges. Diverges. Okay. Similarly, you can show that actually, if you analyze the other endpoint, I will let You do that. I will leave that as an exercise. At when x is equal to 1, series converges. Series converges. Show this, okay? This is an exercise for you. All right, so the interval of convergence is going to be -1 excluded, but +1 included. Let's go over this example now. Outline the steps for finding the Maclaurin series for tan inverse x. Okay, we just have to outline the steps. We don't have to find it. So how do you find the Maclaurin series for tan inverse x? Remember, we are going to use integration to find the Maclaurin series for tan inverse x. Okay, so that means what we need to, the question that you need to ask from yourself is that, can you think of this function as an integration of a function whose Maclaurin series is known? Well, if you look at this particular integral, we all know that integration 1 over 1 plus x squared dx is nothing but tan inverse x plus integration constant, right? You all know that. That means if I have a way to find the Maclaurin series for 1 over 1 plus x squared, then I can put that series here and then integrate that series using the theorem that we discussed in this section, previously discussed. Okay, so that's the idea. So if you can find the Maclaurin series for this function, then we are almost done. Okay, so that's what I'm going to do. How do we find the Maclaurin series for this function? That's not hard, because we know the Maclaurin series for this function, 1 over 1 minus x. That is sigma k goes from 0 to infinity x to the power k. Now, the step 1 is you substitute minus x squared for x in the Maclaurin series for 1 over 1 minus x to find the Maclaurin series for 1 over 1 plus x squared. All what you do is you replace this x by minus x squared to find the Maclaurin series for 1 over 1 plus x squared. Okay, and then here is the second step. Use the same substitution in the inequality. Absolute value of x is less than 1 to find the interval of convergence for the new series. Okay, that means, how do you find the interval of convergence for this series? This is a geometric series. You require your absolute value of x to be less than 1, right? Similarly, for the new series, you need absolute value of minus x squared less than 1, because you are replacing your x by minus x in both sides. Then in that case, you need minus x, absolute value of minus x squared to be less than 1 for your series to converge. Okay, so that's what the second step is about. That will give you the interval of convergence -1, 1, with the possible exception that at endpoints, the convergence of the new series could be different from the original series. So you know that your interval of convergence includes this interval, but you need to figure out what happens at the endpoints. Okay. All right. Now the third step, how do you find the Maclaurin series for tan inverse x? What I do is, I have the Maclaurin series for 1 plus x squared from the step 1. I'm going to plug in that Maclaurin series here. And then I'm going to apply my theorem to integrate the Maclaurin series. You can integrate term by term. That will give you the Maclaurin series for the function tan inverse x plus c. Now you can, of course, find the constant c by plugging x is equal to 0 in both sides. You plug in the plugging x is equal to 0 in the left hand side in the resulting series, and also you plug in x is equal to 0 in the right hand side. That will give you the constant c. Okay, and then finally, as I said earlier, you have to analyze the convergence at the endpoint. Okay, that will complete the steps. All right, let's move on. Next, I want to go over this example. using Maclaurin series to approximate a definite integral. Okay, approximate the definite integral 0 to 1 e to the power minus x squared within 0.001 of its value. Okay, so we need to find an approximation within 0.01 of its exact value. Okay, so how do we find an approximation? First of all, uh, what I'm going to do is I'm going to find a Maclaurin series, okay, for this function. Then I can use my theorem 8.12 to integrate that Maclaurin series. Okay, if I can find the Maclaurin series representation for this function, I know how to integrate that Maclaurin series by the theorem that we discussed. Okay, so can we find the Maclaurin series for e to the power minus x squared? Well, we know the Maclaurin series for e to the power x, right? That is sigma k goes from 0 to infinity x to the power k divided by k factorial. Remember, k factorial is 1 times, 2 times, all the way up to k. The product 1 times, 2 times, all the way up to k. Okay, now if you know the Maclaurin series for e to the power x, can you find the Maclaurin series for e to the power minus x? Of course, yes. All what you need to do is replace your x by minus x squared. That will give you the Maclaurin series. So the Maclaurin series is equal to k goes from 0 to infinity. I'm just replacing x by minus x squared. If you replace this x by minus x squared, you get here minus x squared, and then I'm going to replace this x also by minus x squared. Minus x squared to the power k divided by k factorial. Okay, notice here that if I want, I can apply this k power to each individual term, to minus 1 and x squared. If I do that here, I'm going to do that here itself. That will give you minus 1 to the power k times x to the power 2k. Okay, that's the Maclaurin series. Okay, now I can go with my theorem. So I wanted to remember, I wanted to integrate this function, right? I wanted to find an approximation. This is going to be equal to, let me write it, 0 to 1 e to the power minus x squared dx. Here dx is missing, it's a typo. That's going to be equal to 0 to 1 my Maclaurin series, because my e to the power x squared is same as this Maclaurin series. K goes from 0 to infinity minus 1 to the power k times x to the power 2k divided by k factorial. Okay, now dx, of course, and then I can send this integration inside the sigma notation by our theorem 8.12. Okay, if I send that integration sign inside the sigma notation, you get sigma k goes from 0 to infinity minus 1 to the power k over k factorial times the integration 0 to 1 x to the power 2k dx. That's what you get. Now you can do the integration. If you do the integration, you get, and of course, you have to do the integration and plug in these limits. Okay, I'm going to do the calculation. I'm not going to show the details of the calculation. If you do the calculation, you should get sigma k goes from 0 to infinity minus 1 to the power k divided by k factorial times 1 over 2k plus 1. Which is equal to sigma k goes from 0 to sigma k goes from 0 to infinity minus 1 to the power k times 1 over k factorial times k plus 1. I'm just sending this k factorial over here. Okay. Why do I write this way? That way, if you identify this as your AK, as you can see, this is an alternating series. Okay. Also notice that this AK is a decreasing sequence. AK is a decreasing sequence, and the limit as k goes to infinity, AK is 0. Clearly, the limit as k goes to infinity, AK is equal to 0. Limit k goes to infinity, AK is clearly 0. And also AK is a decreasing sequence. So by theorem 7.37 that we did in section 7.7, we know that this alternating series converges. By theorem 7.7, this series converges. K goes from 0 to infinity, minus 1 to the power k times 1 over k factorial times k plus 1 converges. Okay. Also, by theorem 3.78, we know that first of all, let me take this summation as L. Okay, this converges, and I'll take that summation, whatever the number that it converges to, as L. I'm going to take that summation as L. Okay, then by theorem 7.38, this is 7.37. Okay, pardon me, 7.37. And then by theorem 7.38, we have L minus Sn is less than An plus 1. Okay, L is this limit. L is this limit. What is Sn? Do you remember Sn? Sn is the partial sum, right? Remember, for any sequence AK, Sn is nothing but sigma k goes from 1 to n, 0 to n, AK. You take the n partial sum. Okay, k goes from 0 to. Okay, since you actually start at k is equal to 0, this should run up to n minus 1. And if you start at k is equal to 1, it should run all the way up to n. Okay, so that's the n partial sum. What this means is that n partial sum would be an approximation for L within a minus 1. Okay, the absolute value of L minus Sn is always less than an minus 1. That means Sn is an approximation to L within an plus 1. So we need an approximation to this integration within 0.001. That means I want my an plus 1 to be less than or equal. If I can make sure that my an plus 1 is less than or equal to 0.001, then my Sn will be an approximation to L within 0.001, because this difference is less than 0.001, given this number is less than 0.001. So all I have to do is I need to find the first term such that the least n such that an plus 1 is less than 0.001, and then all I have to do is to get the summation of the preceding terms. Okay, so I need to try out terms here. I need to find the value of an plus 1 for different values. I need to find the least n so that an plus 1 is less than 0.001. So let's do that. It should be an actually, because your partial sum goes from k goes from 0 to n minus 1. All right, so this is the series. If you expand that, you will see that a0 is going to be 1, and then a1 is going to be 1/3, a3 is going to be 1/10, a4 is going to be, right, I listed it down. A0 is 1, a1 is 1/3, a2 is 1/10, a3 is 1/4, a4 is 1/216, and a5 is 1/1320. Okay, I did not write the remaining term because I realized that when I come to here, this is greater than 0.001, but this is less than 0.001. That's what we wanted, right? We wanted to find the least n so that a n is less than 0.001. Now to find the approximation, what you do is you take the summation, this summation. The Sn, that is k goes from 0 to n minus 1, minus 1 to the power k times k times 1 over k factorial times k plus 1. Okay, so what is the n here? You decide n in this case is n is equal to 5, because that's when you realize that your a5 is less than 0.001. Okay, for that particular n, you have to take the partial sum. That partial sum is an approximation to L within an. Okay, so your an is this term, that is n is equal to 5. So you take that partial sum with that n. Okay, remember partial sum, when you take the partial sum, it is from k goes from 0 to n minus 1, because in the original series that you are dealing with, indexing starts at k is equal to 0. All right, now it's all about finding S5. S5 is sigma k goes from 0 to 4. If you plug in n minus 1 here, it's 0 to 4, minus 1 to the power 4, minus 1 to the power k times 1 over k factorial k plus 1. This is going to be 1 minus 1/3 plus 1/10 minus 1 over 42 plus 1 over 216. And if you calculate this, this is approximately equal to 0.7475. So this would be an approximation to the exact value within 0.001. Okay. All right. That completes that example. With that, actually, we conclude that section. I will stop there, and I'll see you next time.